As promised, today we will do something with raster data. So we will need a couple of packages again. Raster, SP, and RGDAL are packages we already used yesterday. So if you installed them yesterday, you don't have to run this line. You can just comment it out. Oops, that's not comment. But by the way, if you didn't know that, you can install multiple packages at the same time using the command, the combine function, sorry, using the combine command, combine function, and then all the names of the packages you want to install. So if you want to install multiple packages, you can do it in one line. You don't have to repeat this line and enter the individual packages again. I'm not sure if the same works for raster, but for library, but we can try it out. Actually, I'm not sure. I think it doesn't work for library, but we can try. We need second parenthesis. Yeah. Okay, so if you try to do the same on library, it gives an error message. And it says package must have length 1. So we can only specify one package we want to activate with library. Alternatively, if you don't want to use the library function, you can go into your package tab, search for the packages you want to activate. And this takes a while because I have a lot of packages installed. Search for raster, for example, and then activate it here with the little checkbox. But we use this library command. But yesterday, we had the issue that the library command didn't activate the package, and we had to manually activate them using the checkbox here. So if you have the same issue, you can fix it like this. Okay, so these are the same packages we used yesterday for the processing of spatial data. And inside of this RGDAL package, there's a function called getData, which is a function to download a couple of data sets that are often used in scientific applications. If we run help on this function, we can see what it does. So it's get geographic data for anywhere in the world. Data are read from files that are first downloaded if necessary. Function C codes returns country names and ISO codes. And then you can download a couple of different data sets, and the one we are working with today is SRTM, if you know that. I think you know it. Maybe you know it. It's a global digital elevation model, and it's the basis for many applications that require topography or like topographic information. So we use this SRTM digital elevation model today, and we acquire that using this getData function later. But first, we need an area of interest. Our area of interest is Bonn, obviously, because that's an unwritten rule when it comes to studying in Bonn, that everything has to be about the city. Every practical application of the software has to be about Bonn. So of course we do it with Bonn again. And the way we handle this AOI is we load it as into our as a shapefile. It's basically the same as we did yesterday, and I think, no, not the day before, only yesterday. We use the read OGR function to read our Bonn shapefile into R. And I think now we have a little issue, and that is our working directory is set to the local repo, but this Bonn shapefile is in the repo for yesterday, so in the folder for yesterday. So we have to use the absolute file path or copy it over. And I think I will copy it over. Okay, so our issue is our Bonn shapefile is in this folder, but we want it in the folder for today. This is the Bonn shapefile. And as you may or may not know, a shapefile consists of several multiple files, a DBF file, which stands for database file. The PRG stands for project, SHX. I'm not entirely sure, but we need all of those files if we want to use the shapefile. So we have to copy all of them. And I copy them into this folder here, which is what we work with today, like this. Go back into R, and now I can use the relative file path, which is much more convenient in my opinion than to find out the absolute file path and put it in here. So I get rid of all this and read it. All right. And then we plot it just to see what we have. And this little plot or map, whatever you prefer, you know already, it's our Bonn shapefile. And these are the coordinates associated with it. And now we want our elevation data. And the way we get this is we use the getData function. I talked about that before. Maybe it would be better to put it like this. Doesn't really matter, but maybe that's more convenient. So we talked a bit about the getData function before. We download SRTM data, which you can just define by giving name equals SRTM or just the name and quotation marks. Yes, you see here in the documentation, you can give in multiple names. You can give GADM for a different data file set. WorldClim is World Climate data file, data set, sorry. And then we have the future climate projections. So there are multiple data sets that you can download using this getData function. And one of them is SRTM. So this is a different way of expressing quotation marks. You can, instead of using quotation marks, you can also use, what's this called? Apostrophes. It doesn't make any difference. It's just a style thing, but please use one of them consistently. So if you decide to use quotation marks, then use quotation marks always to denominate strings. If you decide to use apostrophes, then keep using them. It depends a bit on your keyboard, I think. But don't be confused if you see apostrophes instead of quotation marks. It's the same expression, which is a character or a string. And then we give our latitude and longitude. And this is kind of why we need the X and Y axis in this little plot. It helps us to define where Bonn is in terms of latitude and longitude. So we have a longitude of 7 degrees and then latitude of something up here. 55 is maybe it's a bit big. It will be very big, but it has a reason why it is so big. So we can crop it down to 1 later. So this is, of course, a bit bigger than it has to be. We could also just define like, whoops, still whoops, there we go. We could define like this and it would be more in line with what we want. But I make it a bit bigger now so we can crop it down later. It's part of the learning experience, I guess. So, and we write this SRTM data into a variable called SRTM. And now it will start to download it, the SRTM data. The downloaded data will be put into your working directory. So make sure you have that set correctly. It should be set correctly if you clone from GitHub anyways. But after this download is finished, you can't even see the download window, I think, because it's not part of our, I'm not entirely sure, but there's a loading bar for me right now. Maybe you can see it, maybe you don't. But after this download is finished, we can use our SRTM data. It will take a minute. Of course, we could have downloaded a satellite image or something else, but this is very easy, and we don't have to send you the raster files or something like this way, so you can do it yourself. That's why we decided to do something with SRTM. All right, but if we plot this SRTM data now, we will see it takes a bit longer because it's big or bigger than this one. And nothing happens because the plot window is not great. If we plot this, you will see it's a bit bigger than our shapefile. Yeah, alternatively, if you have a raster already, you can load it into RStudio using the raster command. It works exactly the same as read OGR, for example. You just give a file path. So now that we have it in here in our little project folder, we could also load it in like this. But we don't have to, since we already have it over this variable. You can see that the SRTM variable contains a raster layer, which is something we didn't work with yet, something that's new. So this is a new data type that you know learned of. And what we kind of want to do now, because it saves us a lot of processing time and processing power, is we want to crop our elevation data to our actual area of interest, which is just Bonn. And of course, we could have we could have defined the lat long coordinates more precisely here, and then we wouldn't have this issue. But we wanted to illustrate how you crop a raster data set ANR, so that's why we made it a bit bigger here. And to do this, we use a command called bbox, which stands for bounding box. And you will see what this does in a minute. If you run this command, you will get a bunch of coordinates, min and max coordinates. I guess we could also plot this and it would become even more clear. It doesn't become more clear because it's just coordinates and nothing spatial in there. So the bounding box is a box, the minimum bounding box of a spatial object. So it's kind of a box put around our spatial object and the minimum size. So if I get our Bonn shapefile back, the minimum bounding box would be something like this. And what will happen if we use this crop command on our SRTM data and using Bonn as the thing we crop it with, and this is basically just the same as a clip by vector layer or clip by layer overlay or something like this in ArcGIS or QGIS, is it will take the bounding box and crop our raster according to these bounding box coordinates. That's why we use this bounding box command here now. So we kind of see what the minimum and maximum extent of our raster is. So this is a really easy thing to do. The crop command just crops our whatever we give it with another spatial object. So we want SRTM Bonn, and we assign it the result of our crop SRTM using the Bonn shapefile. And then we have created a new raster layer, which shows up here. If we plot it, it looks like this. So it's much, much smaller. And you can already see the river Rhine here in the middle. And if we add our shapefile, it will become even clearer. And you can see here that it was cropped according to the minimum bounding box, right? Because this is the minimum rectangle, the smallest possible rectangle you could fit around the Bonn shapefile. So now we have cropped our raster, which is nice because it saves us a lot of work and processing time, especially if we have a really big data set. Okay, and now we could export our cropped elevation model using this function here, write raster. This is very similar to writing a shapefile or writing anything else. It doesn't really matter. It's very similar. You just use the function write raster, then you give the data you want to write, then you give a file path and a name, and then you give a format. And in our case, we use the GeoTIFF format. We can get rid of this file path here, I think, because it uses relative file paths. Let's check what happens. All right, you can see here, and we are still in the same folder. We have a new file here called srtm.bonn, and you can already see the file difference between those files here. This one is 70 megabytes or 70,000 kilobytes, and this one is barely 1 megabyte large. Yeah, one thing we often do when we have topographic data is calculating topographic metrics such as slope and aspect. I'm sure you did this before for some sort of terrain analysis. That's also super easy because there is a very powerful function called terrain in the raster package. I don't know if it's in raster or GDAL. And this terrain function allows us to compute terrain characteristics from raster with elevation data. I think the most common ones are slope and aspect, obviously, and that's what we do here too, but there's other metrics you can calculate, I think. Anyways, if you're interested in what you can do with this terrain function, you can read through the documentation. I think it's rather descriptive in this case. But we use it now to calculate slope and aspect. And the way you do this is also very, very self-explanatory. Use the terrain function on your data set. You define what you want to have calculated, and then you define the unit. So in our case, we use the unit degrees, and there's also radians. There's radians or tangent. This is only relevant for slope and aspect, it says here. But yeah, let's do that. Write it into a variable called slope. We can plot it. So now we have a map of our slope where you can see the steepest slopes. And I don't know what the opposite of steep is. the flattest slopes. I don't know. And conversely, you can do the same for aspect. And have it look like this. And this is degrees, right? So think of it as a clock or a compass. You have 360 degrees because it's a circle. And from this aspect map, you can see which slope has a northwards or southwards or westwards or eastwards exposition, which is important for some kinds of terrain analysis. And I think the way this is going, so what's our goal here is to actually conduct a small, a tiny spatial analysis by reclassifying the slope and the aspect, and like finding areas that are good for vine growing, which is a very classic example for terrain analysis, I think. And we want to find, yeah, not regions because we are in the region, but places that are good for growing wine in this small area of interest of Bonn. I don't know if you know it, but there's actually wine growing in Bonn. There are some wine slopes. The wine tastes not great. Terrible, in fact. That's my personal opinion. But Bonn is one of the most northernmost regions, I think, where wine growing is still a thing. Because I found out that Zoom has a whiteboard function and I really want to use it. But usually this gives students a headache. Probably not you because you did it before, I think, I'm pretty sure. So the idea behind this is rasters are basically tables, right? Okay, this looks more like a botched chocolate bar. But a raster is basically a table, and these tables have pixels. So each little square is pixel, and these pixels have values. In our case, these are degrees for aspect and for slope. So if this is aspect, this might be 260, 260, and so on, 180. And then we have the second table with elevation data, derived from elevation data, sorry, that has slope, and the slope is something between 0 and 90 degrees, even though we probably don't have 90 degrees slope anywhere. And then we have something like this, which is not realistic, but whatever. And we want to find regions that are good for wine growing. So we basically find out what slope and aspect are good for wine growing. And then we find out wine needs a southeast or something like this exposition. I think the slopes have to be exposed into a southern direction because it's the direction that receives most of the sun throughout the day, and wine likes it really sunny. And that's why we want only southern slopes. So we kind of check what kind of values here are southern. And then we find out that, for example, maybe 140 to 250 degrees as southern. So we want these values to be 1, and everything else we want to be 0. And then this raster after reclassification looks something like this, right? Because we reclassified all the values, it will look something like this. Like this. And the same we do here. We look what slope is cool for wine growing and which slopes aren't, because it can't be too steep, I think. And it can't be too flat because it has to be exposed to the southern direction, at least here in the north. I'm not sure how it's in regions that have abundance of sun exposition. And then we have a second raster like this, which looks somewhat similar. And then if we multiply those, we get a raster that still has zeros and ones in it, but because 0 multiplied by anything will inevitably become 0, we have a raster where only the good pixels will remain as 1. It's rather simple. even though it looks complicated at first. First, we have to create a list that is structured like this. So we use the combine function to create a list. Maybe let's give it the name reclassification list instead of X. And then we have to define our reclassification values. So we want everything from 0 to 10 to become 0. We want everything from 10 to 45 to become 1, and everything from 45 to 90 to become 0. And this is for slope now, right? So these are slope values. So we want 0-degree slope to 10-degree slopes to become 0 because we don't want it. It's not good for growing wine. We want 10-degree slope to 45-degree slope to become 1 because it's good for wine. And then we want 45-degree slope to 90-degree slope to become 0 again. This is basically the idea behind this list. And if we give this list to the matrix command, which we already used in, I think, 2 lectures, and say we want 3 columns, and this is the ordering command. Actually, let's call this slope reclass list. Like this, and let's call this slope reclass table. So we turn this list into a table, but first we have to create it. So now here you can see our slope reclass list is a list, it's a vector with 9 values in it. Now we turn this into a table using the matrix command, and then you can see here slope reclass table. We can look at it in the table viewer. Looks like this. So we have 0 to 10 is 0, 10 to 45 is 1, and 45 to 90 is 0. And this is just a reclassification table like you would have one in ArcGIS or QGIS if you were to reclassify by table. And then we can reclassify using the command called reclassify. And the reclassify command requires a data set to reclassify, and it requires like kind of instructions of how to classify. And this is where we pass this table here. So to reclassify, it's called like this, slope reclassified. To reclassify our slope, we use the reclassify command on slope by slope reclass table, which is our reclassification table. Then we create this new raster layer here, and if we put this, it will look like this. So in this raster layer, you only have 2 values, 0s and 1s, and the 1s are green in this case. I think it's green, yeah. And the 2s are 0s. So basically what happened here is all the slopes that were between 10 degrees and 45 degrees became 1, and everything else became 0. And now we want to reclassify our aspect, which works exactly the same way with one tiny difference. And the difference is the values we have to define as 1s and 0s inside of the reclassification matrix are different now. And these values, I think, are subject to discussion. So you would have to base them on, I don't know what people who actually grow wine say it's good for wine. And these are a bit arbitrary. I'm not claiming this is actually the way to go if you want to do spatial analysis to find wine growing regions. So this is something that is probably more explored by people who actually work in this field and actual research on the subject matter. But for our simple explanation example, it's fine to assume that these values are okay, at least okay. So we want to reclassify our aspect. And if we take a little look at the reclassification table, we want our aspect to be reclassified according to this table. So 0 to 112.5 degrees, which is east, northeast, east and northeast, and a bit of southeast, I think, but only a bit. We want this to be 0 because we don't want it. We only want southwards facing slopes. And 112.5 to 247.5, we want to have reclassified as 1 because these are south slopes, southeast slopes, and southwest slopes. So if you remember the windrows we had before, you could visualize this in your head. And then all the other slopes that are east and northeast, we don't want them either, so they become 0, 2. And the way we approach this is exactly the same as we did before with the slope reclassification. So I will rename those variables accordingly, so it's a bit more cohesive. This list is our slope reclass list, and this matrix is our, not slope, aspect, sorry, as our aspect reclass matrix, or no, table. We said it was a table, I think. Yeah. And then we reclassify using the reclassify function, using the aspect reclass table. We run this. This is supposed to be the aspect reclass list. And now it's correct. And if we reclassify this now and plot it again, it looks correct. Thank you very much. So we have two values here. We have 0 and we have 1. And 1 are the southwards facing slopes, and 0 is everything else. Okay, and now we want a raster that kind of combines these two informations. And this is very easy to achieve. We can just multiply the two rasters because they are just tables after all. So each, of course, they have the same extent too. That's good. Each pixel and side of these rasters will be multiplied with each other, and this will create a new raster in which everything in every pixel where both our criteria are in favor of wine growing will be 1, and everything else will be 0. Just due to the nature of multiplication, quote unquote. We call this raster wine growing, and then this is just simple math, right? We take one raster and multiply it with the other raster. And then slope reclass is not found because I changed the name to reclassified, and I will do this here too. And then we have to change it here too accordingly. And then I run all this again. And this part, and this works just fine. If we plot it now, we can see the areas where both of our criteria were 1. So these are the slopes that were, at least when slope and aspect are concerned, that are fine for wine growing. And I think this one down here is actually used for wine growing. The others I'm not so sure about, but I think this one down here, there's a wine field, a wine slope on it. To make this a bit more clear where we are, maybe we add our Bonn shapefile. But of course, aspect and slope, this is just a small example that we kind of dumbed down a little, so we downscaled it a lot. In an actual terrain or raster analysis, you would have to consider much more criteria. Of course, wine growing isn't entirely dependent on the aspect of the slope the wine has to stand on and the slope. There are other criteria that are important, stuff like soil, for example, and precipitation. And I don't know, I'm not an expert on wine, but just so you know, this isn't 100% accurate probably. All right, but now we have results and we want to export our results to a local folder. We can easily do this because we still have the working directory in our local folder here. Yes, it's still there because we didn't change it. So we just write it into, we write our data set, wine growing, into a file called wine growing TIFF and format GeoTIFF. And if we run this and look here in the files, you will see down here we have the wine growing TIFF. And now we could import this into, let's say, ArcGIS. But now we have a second thing, now to something completely different. We have a second data set in here. It's somewhere, where is it? There we have it, which is called Corona-Zahlen-Bonn 27052 and 1.csv, which is a table with COVID case numbers. Let's get this data set into R and have a look. We assign it a variable called COVID data. Now you can see it's a bit messy and full in our environment. Our environment is a bit messy and full, and it's like hard. It's getting hard to see what we have loaded in right now. But somewhere here, it's ordered alphabetically. So somewhere here we have the COVID data. Let's have a look. This data set has a couple of columns. The first one is some statistical ID that's not really important for us. Then the statistical unit, which is kind of district. Then we have the population number of this statistical unit. Then we have how many cases we had each 70-day span. So every 7 days we had, for example, in Bad Godesberg North, we had 11 COVID cases. Then we have an incidence number, and this is just, I think, the day where the data was registered or recorded, not entirely sure. This is our Corona-Zahlen-Bonn table. And then we have another shapefile here, which is called Bezirke Bonn, which means districts of Bonn, which is a bit like our Bonn shapefile, but granular. So we have the little districts in there. I will just load it in and show it to you, and then it's much clearer. We have to read this using read.ogr because it's a shapefile, it's spatial data. Cannot open data source. And the reason why is because this isn't called districts. Unfortunately, it's called Bezirke. There we go. Now, if we plot this, it looks a bit like our Bonn shapefile, but with the districts, the neighborhoods, so to speak, of Bonn in it. And what we want now is we want to perform a table join, because in our COVID table, we have a column that includes the district names. And in the attribute table of our Bezirke Bonn, we have the same column. So we kind of want to join these two data sets. and like get our COVID numbers into a spatial format by performing a table join. And first, let's take a look at, I remember, okay, we don't perform the table join by the column, by the district name, but by the district statistical ID. Apparently Bonn uses for each district a statistical ID. So Ökostor, for example, is 128. And this statistical ID, I said before it wasn't relevant, but apparently it is. It is relevant. We use this column here to perform our table join because we have the same statistical IDs inside of our districts data set. And this is a new way of referencing a data frame with the @ sign. If you have a spatial data frame, in our case, a spatial polygons data frame, but it could be spatial points data frame, doesn't really matter. You can reference individual parts of this data frame by using the @ sign, and data is, in our case, the attribute table. So we had this question yesterday and I gave a longer and more convoluted answer, I think. And I even like gave code to calculate this attribute table by yourself. But the way easier approach to do this is just by using the @ and then the data. And of course, this might have different names for depending on your spatial data set that you're using, but you can see the data type here. So this is a table, and these are polygons. Okay, but this is our table, and we can kind of see it's similar to this column here, which is called statistical ID. Maybe if we order it like this, it becomes more apparent. So just have a look at here and then up here, and you can see it's the same column. All right, and now we perform our table join, and we do this by using the merge function. The merge function is used to merge data sets in general. It's not just spatial data sets. So you see here, merge has several meanings or several definitions in the documentations. And one is to merge a spatial object having attributes with a data frame, which is exactly what we are doing right now. It's a function in Raster package, in package SP and not in Raster. Then we have merge raster objects, which is in Raster, and then we have merge two data frames, which is part of the base functionality. So in our case, we do this here. We merge a spatial object having attributes with a data frame. Our data frame is Corona-Zahlen-Bonn. Our spatial object is districts Bonn, and we want to merge them together. And to do this, we use this merge function here. First, you define what data you want to merge. We want to merge the districts, and we want to merge COVID data. And then you have to define which columns inside of the attribute tables or inside of the data frame are the merge columns. So you need one column that is identical to perform this merge. In our case, that is the statistical ID, and respectively the statistics column in the spatial polygons data frame. And you define this by using by X and by Y down here. Specification of the common columns. So you need two common columns, one in each data set you want to merge. Yeah. All right. So we run this. And then we create a new data set, which is called COVID-Bonn. And if we look into our COVID-Bonn at data now, into the attribute table, you will see it is much bigger because it now contains all the data of the COVID data set. So this is a very convenient way of assigning data to spatial data. But it only works if you have a merge column. So something like a statistical ID, something like a name. Often you have to, often you have to create your data yourself and create this merge column, which can be very tiresome. But in our case, it was very easy, and I think it's very clear what this did here. Okay. So let's create a map. Let's first look at the chat. Okay. Let's create a map, because having this as a table is fine and dandy, but you know, we are geographers and we want maps. And the way to approach this is, this time we don't use plot. And that has a very simple reason. The reason is plot is good at plotting base data, like data frames, for example. But the plot function wasn't designed in mind to use with spatial data. And so this function here, spplot, is from the sp package, which is a package that is all about dealing with spatial data. So it's a spatial plot function. It's basically the plot function, but adapted for spatial data sets. And you can see, if we open the help window, spplot plot methods for spatial data with attributes, which is exactly what we have now. We have a spatial data set, Geo.Info.Bonn, and inside of this spatial data set, we have a bunch of attributes, which are these COVID case numbers, Fälle 7 Tage, each 7 days. The incidents, or yeah, or the case numbers. So these are attributes with a spatial reference now. They have a spatial reference now. So we use this spplot function to plot them. And first, let's run the plot. Let's run this function just like this. Just run spplot on Geo.Info.Bonn just to see what we get. And the result looks like this, which isn't very nice, but it's a map. So what we see here is a plotted incidence. Let's go back in, let's get up into the table. If you remember, one column inside of this COVID data frame was called incidence, which is incidence. And this is what we plotted here by giving this name. So if we give Fälle 7 Tage, for example, it will plot the cases. Looks like this. You can see the scale adjusting. It doesn't look that much difference because the cases are directly tied to the incidence. It's just the scale that was adjusting mostly. We can also plot maybe the name, but then every tile in here will get a different color because it's a qualitative. Yes. So you see here a giant legend, and then each district gets a different name. But we want to plot incidence, which is a bit different from kind of what you're used to do in the basic plotting function. So if you remember when we plotted before, it was something like COVID-1, and then we took the column we wanted using the reference, the $sign indexer, and then we used like this, for example. If we run this, we get a scatter plot. But since we can't index individual columns of this attribute table using the $sign anymore, because it's no longer a data frame, but a spatial polygons data frame, which is structured a bit differently, you call the column here using just this string. Okay. So this is already a nice map, or it's a map. I wouldn't call it nice. You also have some plotting options that are similar to the ones in the normal plot function. So if we add main COVID-19 incidence 1, then we get a title like this. This is relevant, I think. Okay, so but this is already a map, but the map would be nice, but the color scheme looks terrible. If we are honest with ourselves here. And we already learned one way to deal with color schemes, or how to define your own color scheme yesterday. So we could go ahead and do this again and do it like yesterday, but today we learn a different way to approach this. And that is using a package called rColorBrewer, which is based on the ColorBrewer website, if you know that. First, of course, we have to install it. I think I already have it installed, but I will just reinstall it for you. And then we call it with library. And inside of this ColorBrewer package, there are already a couple of predefined color ramps that you can just use, and you can display them in your plot window using this little function here, display brewer all. And then you see all the different color ramps that you have access to using the ColorBrewer package, and the names, which are somewhat important because you need them to specify. So here we could pick one suitable color ramp for us. I think in our case, we choose the first one, yellow or red, YL or red, because it's a nice color scheme, I guess, for a pandemic map, because it's red and like threatening and sequential. So it's the same color all over again, just in different use. And this function, ColorBrewer palettes, creates nice looking color palettes, especially for thematic maps, using the ColorBrewer function package. So you use this function here, you define a color ramp. Let's call it my color ramp. And then you give how many classes you want inside of this color ramp. So if we give n equals 2, then we get 9 different colors inside of this palette. The minimum is 3, and the maximum depends on palette. So some palettes don't have 20 colors, some are longer than others. You can see this here. Set 3, for example, has more different colors inside of the palette than, for example, the yellow or red one we are using right now. And then you just give the name of the palette you want to use. And that defines our color ramp. And then you can see here, we have a new value inside of our environment, which is called my color ramp, and which is a vector with these hex codes for the individual colors. And now we can use this inside of the sp-plot command. Oops, I didn't want that. I wanted this. And inside of the sp-plot command, by using the argument color regions, and then we assign our color ramp here, which is now called my color ramp and no longer my color. And then you give the amount of cuts that you want. And these are the color cuts. So we plot this, and then we get a nice plot with a better color ramp than before, which shows the COVID-19 incidents in Bonn. So to be probably, it should be, I think it would be good for the map to add a date on top. So maybe, I think this one is the date 2070. So let's add this to the name. And run it again. What's not? I was in the wrong line. Sorry. Let's see here, this one. There we go. And if we can play a little bit of the breaks, just to see the difference between 6 breaks and 8 breaks. So this is just how many colors will be on the map. The maximum is of course 9 because our color palette only has, it's 8, sorry, because our color palette only has 9 different colors. So it's always the maximum amount of colors in the color ramp -1, obviously, because it's the cuts in between. So if we define 12, for example, we won't have enough colors. So you can see here, the colors keep repeating, making the map very unreadable. But 3, for example, is the minimum. Looks like this. Let's take 8 for now to have maximum differentiation between our classes. Okay. And then we have one more cool thing about the SP-plot function. You can add more than one layer by using an argument, which is called SP layout. And inside of these SP layout, you have to give a list. And inside of the list, the first item is the data type you want to give. In our case, that's a bunch of points. The second item is the object we actually want to plot, and everything else is more plotting options for that. So you can add more than this one single layer here. You can add, for example, a couple of points. And these are supplied by us. So I just read them in here, called points. Cannot open data source. Because it's from yesterday, I think. So if you remember, yesterday we had a bunch of coordinates. I think it was 8 coordinates pairs. And we converted those coordinates into a spatial layer called Points.Bonn. And this is what I want to load into R now. So I copy over these little points into my folder. And now you can see them down here, our Points.Bonn from yesterday. So now we should be able to load them in just fine. Okay. Yes, like this. Now we have our layer points. And now we define the list that we will call in the SP layout argument. We do this just by using the list function to create the list. It's very self-explanatory. And the first thing we have to define is the data type. And in our case, that's SP points. You can see this up here, spatial points. It's spatial points data frame. So SP points. Then we give the data we want to have in the list. we want to add to our plot, which is points. And then we give them a color. In our case, that's black, but you can do whatever you like. And then we add this SP layout argument to our plot function. And I add the date. And plot object layer is not found because I didn't run this. Whoops. My color not found because it's not my color, it's my color ramp. There we go. And now it should work. All right. And what you can see here now is that our points, these little crosses, are added on top of our layer. Yeah. And that's it, I think, for the SP plot function. So the SP plot function is basically like the plot function and base hour, but for spatial data that has an attribute table under it. Very similar to the plot function, you have a lot of different ways to change the visualization of data in here. So you can absolutely create maps using vector data or raster data in R. Sometimes it's good, sometimes it's a good approach if you have simpler data sets. But sometimes it feels limiting, especially compared to the print layout options in something like a GIS, for example. So it's up to you to decide whether you want to create your maps in R or whether you want to create them in a GIS. But technically, R is perfectly capable with the use of plugins to function as a GIS. It's just sometimes it's a bit more inconvenient.